Welcome to Biomaterials. Today we're going to talk about condensation polymerization. And we're going to break it up into a few topics. So the first topic we're going to talk about that relates to condensation polymerization is what type of configurations can we have for the monomers that make up the that will eventually combine with one another to make up the chains of polymers. So monomer configurations. And in essence, there are sort of two main modes that you can have for condensation polymerization. You can have a single type. You can sort of do condensation polymerization where all of your monomers are of the same type, or you can sort of have a paired combination where you have an equal number of two different types of monomers, and you can eventually you can basically combine them in a sort of alternating fashion to build up chains as well, and both modes can result in condensation polymers. Then I'm going to give some examples of a few common condensation polymers. And you'll never be expected to memorize the molecular diagrams or the reactions or things like that. But I just wanted to sort of make you aware of, like, when you're walking around in your everyday life and you encounter some certain, someone says, oh, blah, 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 blah. It's nice to sort of at least have in the back of your head a picture of what's going on, at the molecular level. So some examples include polyamides. And they sort of have another name, polypeptides. Another example of a condensation polymer that we'll talk about are polyesters. We'll also talk about polyurethanes. We'll also talk about silicone, which sort of has the more formal name polysiloxane. And a specific example of a polysiloxane that you might encounter, particularly in microfluidics or other applications, is PDMS, polydimethylsiloxane. And then one final polymer that we'll talk about are polycarbonates. Then, once we've talked about a few examples of polymers that are formed via condensation reactions, we'll do a bit more of a comparison between condensation and radical polymerization. So condensation between condensation. So radical is what we talked about in the previous lecture. Condensation is what we're talking about today. We'll sort of do some compares and contrasts to sort of compare them, how they grow, what are some features, and what are some features that engineers can exploit in each sort of polymerization reaction type. And then I'm going to introduce a new term, which is called the degree of polymerization. And I'm going to introduce some equations that can be used for condensation polymerization to sort of characterize a relationship between the molecular weight, m sub n, and this degree of polymerization, p, which sort of describes completeness. So we'll basically say, hey, can we essentially get a relationship between how complete our polymerization reaction is, because no chemical reaction can ever be driven all the way to completeness, and what might be the molecular weight of the polymers that we've created sort of so far in that polymerization process. And then this idea of, hey, maybe not all polymerization reactions are going to go to completeness, we'll sort of talk about the trade-off involving time. So time versus molecular weight trade-off. And basically, if you want higher molecular weight polymers, you're going to have to pay for it by waiting a long time for that reaction to occur. So without further ado, let's get started with talking about the two types of monomer configurations that might exist in these reactions. So the two main types of monomer configurations that you can have, well, one is if basically all the same, but two different functional groups per monomer. Two different functional groups per monomer. And what might that look like? Well, the way I like to think of these types of monomers are like Legos. So there are essentially two reactive groups in a monomer. You can think of it like the Lego bumps and the Lego holes. And you can imagine if I had a whole bunch of monomers, and each monomer has one bumpy side and one holey side, then these monomers can eventually, every time a monomer joins a chain, it sort of refreshes the reactive group that then can go with another chain. We don't even need to sort of have a single chain that's growing with all of these. Again, remember, you can form dimers. Monomers can join up to form dimers. More monomers can join up to the dimers to form trimers. Dimers and trimers can join together, and you can sort of grow, just everyone growing with everyone, in one big happy family. So the key thing here is we have these monomers where there are sort of two functional groups per monomer, right? So we might say, hey, there's one monomer here with some group, let's call it A, sticking off one side and B sticking off the other, and then its neighbor also has a B and an A. These two monomers are identical to each other, and the A and B can essentially react. These react to form a covalent bond, and then there's another A that could react with another monomer, another B that could react with another monomer, and the cycle continues. The alternative to this having them all be the same is if you have difunctional monomers. And two types. One with two of your, let's call it like your A group, two A groups, and then your other with two B groups. So what might that look like? I had to sort of make some weird Legos in order to do this, but you can imagine, if I could, just imagine that there's no tape here, right? Imagine that it's basically, a single unit. I can essentially, if I had, some molecules that looked like this and some molecules that looked like this, when they join together, they're going to sort of form an alternating chain where I have this type of monomer, then this type of monomer, and this one, and this one. And provided I have an equal number, provided I have an equal number of this type and this type, I can then just sort of continue my chain on and on and on. So, so what's that going to look like? Well, I essentially have A, and B, B, and as long as I have an equal number, then they can sort of react with one another to sort of form this alternating chain. So if I have an equal number of each, they alternate to form chain, where I would have an A, a B, and then another A, and these react with each other to form covalent, covalent bonds. So that's basically, and then then I basically have formed my chain, my chain that looks like this. And these can, these can grow sort of in a step growth way that was similar to these ones as well, right? I can have, this little chain grows up by itself, this little chain grows up by itself, and then these partially formed chains react with one another to form much longer chains. That can happen with this process as well as this process. So basically both of these processes grow via condensation reactions. Both of them grow in a step growth way. It's just what types of monomers do you have, right? And when we talk about when we move forward to talk about all of these examples, some of them will come from this category and some of them will come from this category as well. And right now I'm kind of generalizing, these ideas as A's and B's, but when we talk about these type of polymers that form and the type of reactions that form them, we'll give specific, I'll assign specific chemical groups to like A or B. For example, let's start talking about polyamides or polypeptides. So if you asked a polymer chemist, they would call them polyamides or polyamides. And if you asked a biochemist, they would call them polypeptides. But, they're really the same thing. And so how are they the same? Or, what types of bonds, what types of chemicals are involved? Well, imagine I have one growing chain or one growing monomer, and it has an it has an NH2 group. So this is an amine group. Has a special name. So this is what we'd call an amine group. So we'd call an amine group. And if there's some other chain that on its end has a carboxylic acid group, well, if you dust off your high school biology notes, you would know that these two groups can react with one another to form a bond. And this is the way that amino acids grow into proteins in our body. So these react with one another. So we have whatever was growing over here, and an N and H. An H and an OH react with one another, leaving a covalent bond to the carbon. There's still this double bonded O out along for the rides, and basically whatever is going on here And of course, if you count up all the atoms here and count up all the atoms here, you'll realize you're missing an H2O. So there's plus 1 H2O that's kicked off in this reaction here. And basically, this is the way that amino acids are synthesized into proteins. So for example, amino acids basically have some interesting molecular stuff going on in the middle, but the key thing here is they have an NH2 sticking out of one side and a COOH sticking out on the other. So basically these amino acids, one amino acid forms this, and then another amino acid comes along and forms another one and another one and another one. So these amino acids like this build up into long chains of proteins. So this, so amino acids are an example of that first configuration of monomers, where each monomer has one of one type and one of another type in its to form its reactions. These are not the only polyamides that can form. You can also form polyamides of another type. You can also form polyamides of this type as well. So you could have essentially, one bucket of things that, for example, have 2 amine groups on them, and you can have another bucket of molecules that have 2 carboxylic acids. So an example of a molecule that forms sort of in this type with, an equal number of 2 different types of monomers that are each difunctional with one group, and then the other one difunctional with the other group, is nylon. And there are actually a couple different types of nylon. So the one I'll talk about is nylon 6,6, which basically has these 2 molecules. So there's an NH2, and then 1, 2, 3, 4, 5, 6 carbons, and then another NH2. And this one is called it's like hexamethylene diamine or something like that. I don't remember the exact name of it, but you can imagine there's this type of molecule, and we might call this sort of analogous to this, and then you could pair that with an equal amount of COOH. So that's 1, 2, 3, 4, 5, 6 with another COOH. And I think this one's called adipic acid. So there's hexamethylene diamine and adipic acid, and as long as you have these in equal ratio, we have one of these, then one of this comes along, forms an amide bond, and then another one of these comes along and grows that way. And every time every time these react with one another, it's sort of we get an alternate from one molecule or one monomer of this type and one of this type and one of this type and one of this type. So they all react together. The nylon 6,6 specify the number of carbons. So there's 1, 2, 3, 4, 5, 6 carbons, and then there's 6 carbons. 1, 2, 3, 4, 5, 6 in this one. There are other types of nylon. For example, there's a nylon 610 and a nylon 612. And they have different numbers of carbons between the nitrogens, or between but including the carboxylic acids. So you might see that there. So where might you encounter polyamides or polypeptides? Well, a lot of your clothing might have nylons in it. You might have people like to wear nylon stockings, with skirts and dresses and things like that. Polypeptides are, of course, all over the place, right? They make up the proteins in our body, both structural and functional. These little straps are made of leather, and leather is mostly collagen, and collagen is a polypeptide. So here's a polyamide right here. And actually, I didn't even really need to bring this out as an example. What you're looking at, my hands right now are full of polypeptides. So there we have it. let's now talk about polyesters. Oh, actually, sorry. One more thing. To go back to what I have here, these polyamides can form with a COOH. There's also another. Instead of having a COOH right here, it can be or what's called acid chloride. Or acid chloride, which is a COCl. So instead of having an OH group, there's a chlorine hanging out right here. So, and basically, when it reacts with an acid chloride, it still forms the same bond, but instead of kicking off an H2O, the H here reacts with the Cl to form +1 HCl as the byproduct of the reaction. So, you can have amine groups reacting with carboxylic acids, or you can have amines reacting with acid chlorides. Both form the same type of bond. It's just the byproduct is different for the two. All right, now on to polyester. So, if I were to give this lecture live, the day that I give this lecture, I would wear some very cheap polyester suit and talk about polyester and how it's useful. But whatever, you'll just need to imagine me in a polyester suit right now instead. Sorry to disappoint. The ester bond, is a reaction between two groups, and it looks like this. So we have some growing chain, and on one side of the growing chain, we have a carboxylic acid group. And then in another part of the growing chain, instead of having an amine group, we just have an OH group. So we still have carboxylic acid. And then we have what might be called hydroxyl, or might be called an alcohol group right here. So these react with one another to form the following: COO, and then it just sort of continues along. So take a moment now, pause and ponder. What's the byproduct of this reaction? Well, if you tabulate your atoms, you'll realize that the byproduct for this reaction is also 1 H2O, and that's basically what forms. So one interesting thing about polyesters is no chemical reaction is sort of a complete one-way street, right? So these react, the forward reaction is very strong, but we also have a reverse reaction happening too, right? There's a K forward and a K backwards. So periodically, these bonds, if they're exposed to water, the reverse reaction can happen. If water's present. And that can occur, for example, in bees. So you might have seen, 100 these plastic cutlery, right? Like it feels plasticky. You can't see it here, but it says 100% compostable, 100% made from plants. So what these are actually made of a biodegradable plastic. These biodegradable cutlery, not all plastic cutlery, but the slightly more expensive compostable plastic cutlery, are made of polyesters, and in particular, I think they're made of polylactic acid. So biodegradable cutlery is made of polylactic acid, which looks like this. There's a COOH, then there's a C, a CH3, and an OH right here. And if you look at it here, there's the OH right here and the OH right here, and there's this COOH right here and a COOH right here. So basically these groups, we can have lactic acid, and these lactic acids can just join up and join up and join up and form chains. And the nice thing about this biodegradable is, the forward reaction happened, reasonably quickly during the manufacturing process. But basically, once I put these in the compost pile, they'll then be exposed to the moisture in the air and soil, and that water can then attack this ester bond and degrade it back into its constituent monomers. And these lactic acid molecules can get taken up by soil bacteria, fungi, etc. Polylactic acid, or PLA, can also be used in like 3D prints. Some 3D printers print in PLA and stuff like that. And it's great, right? It's cool to have biodegradable polymers, from an ecological standpoint. PLA is also being used inside our bodies as well, right? I'm pretty wet on the inside. I'm made of blood and a whole bunch of other fluids. So polylactic acid can be used for degradable polymers that are used inside of our bodies as well. And so basically, as long as there's H2O present, we can get some of the reverse reaction going on as well as the forward reaction. So 3 cheers for polyesters. Of course, not all polyesters are as biodegrade as rapidly as PLA. Some other biodegradable polyesters, for example, PET, like that makes up plastic soda bottles, is, it's still a polyester. It's just that the reverse reaction is much more slow for PET, compared to PLA. So, still biodegradable, just over millennia instead of over, a couple of weeks or months. So that's the usefulness of polyesters and what makes up their bond. So, what's the key thing here? If you see a carboxylic acid and an alcohol, they could probably react to form this. And in contrast, polyamides, there's a carboxylic acid reacting with an amine group to form a bond that looks like this. So now let's talk about polyurethanes. So you might have heard of polyurethane. If you took a little tour into my basement, you might see, well, you'd see a terrible mess, but you might see some foam sealing up, part of one wall to part of the brick exterior, and this foam right here is essentially an expanded polyurethane foam. So you might see polyurethane showing up. You might have seen like a brand name is like Great Stuff Foam. Great Stuff Foam is one example of polyurethane. Of course, polyurethane isn't one specific material, but rather a class of materials that all contain these types of bonds. So you basically have some group that looks like this, and then there's an N double bonded to a C, and that C is also double bonded to an O. And this somewhat bizarre molecular motif right here reacts with an alcohol group to form the following bond. Again, it's a little bit wacky, but bear with me. An N H single bonded to a C that has an O like this, single bonded to an O that then sort of goes along like this. So take a moment now, pause and ponder. What byproduct? What byproduct might be formed in the condensation of polyurethane? Well, if you do your molecular bookkeeping, you might realize that there's actually none. Right? All of the atoms that started out get used up, and sometimes that's useful, right? Sometimes it's useful to have a polymer be able to form without needing to worry about how you're going to extract all of the water or extract all of the hydrochloric acid from that reaction as it's happening. Now, an interesting thing about polyurethane is if I were to look at it just like this, if I were to look at this part of the urethane bond, what would that look like? Take a moment now, pause and ponder. What does this part of the urethane bond look like? Well, if you look at it, this part of the urethane bond looks like a peptide bond or an amide bond. What about this type? Well, this looks like an ester bond. So in a sense, this looks like it sort of has amide-like properties, and it has ester-like properties in it as well. And there are many different types of polyurethanes, and again, I'm not describing at all sort of what happens in these regions between the urethane bonds, right? You can have any number of wacky things going on in these, in between the urethane bonds. But describing something as a polyurethane basically means its bonds are sort of this like double combo of an amide and an ester-like quantity. Let's now talk about another type of polymer called silicone, or you might call it a polysiloxane. So let's say I had some polymer chain, and so far we've really only been talking about polymer backbones that have been made of carbon, but imagine here I had a silicon and a chlorine, and the silicon had two CH3 groups on it. And then this encountered another molecule of the same type, or sort of another functional group of the same type, CH3, CH3, and a chlorine. So these two reactive groups came close to one another, and I also threw in the mix two H2Os. Well, what would happen right here? Well, basically, in the presence of water, these two things can react with one another, and you end up with a silicon, CH3, CH3, and oh, sorry, not two H2Os, just one H2O in the mix. Sorry, just only one H2O. A silicon, oxygen, single bonded to a silicon, CH3, CH3, right here. And then as a byproduct, these two chlorines basically react with these hydrogens right here to form two HCl. So this kicks off hydrochloric acid as a byproduct. Now, you might have encountered silicone in your everyday lives. Silicone caulk is that sort of white gooey stuff that seals off the edges of your bathtub against the edges of the ceramic tile or whatever else is around your shower or bathtub. What's nice about silicone is basically in the tube I just have a whole bunch of molecules that look like this: silicon, CH3, CH3, and then I might have like two chlorines on the side right here. And basically once this silicone is squirted out of the tube and reacts with water vapor in the air, that water vapor then kicks off this reaction process. So, in terms of convenience, it's nice to have a polymer that sort of, when it's sealed off in the tube, remains non-reactive, but as soon as it's exposed to water, like that sort of sets off the curing process. And you know, all of these silicone monomers can then join together to form some chains. What's an interesting thing about silicone is, if you imagine, if I used molecules like this, if I used molecules that looked like this, the entire backbone could be made of nothing but silicon oxygen bonds. And if you can imagine, like, silicon dioxide is essentially one of the major constituents in sand. And, like, you know, sand it's like a dead end molecularly. Like, right? Good luck trying to break apart sand. So sand is one of the most, like, stable, you know, silicon dioxide is one of the most stable things here. And these silicones are super duper stable, right? So entire backbones, these are more stable than like carbon-carbon bonds or carbon-oxygen bonds that we had formed here, right? So all the polyurethanes, polyesters, polypeptides, you know, all of those, you know, if you heat them up enough, they break down. But for example, silicone, you know, here's a silicone spatula that I got from my kitchen. Silicone rubber is basically what makes up this thing here. This silicon oxygen bond is super stable. I could practically put a blowtorch on this silicone spatula, and it would remain, you know, chemically stable. I might start reacting some stuff with the CH3 groups, but the silicon oxygen backbone is so stable that, you know, that you can heat these up to hundreds of degrees and they still remain stable. So for certain applications, you know, these silicone rubbers, you know, high temperature applications, they're also pretty resilient in our bodies as well. Silicone rubbers are used for lots of implants. For example, breast implants, you know, are oftentimes made of silicone because these bonds are pretty resilient to the sort of chemical attacks that our bodies would put on them anyway. So there's a use for that. PDMS, or polydimethylsiloxane, is basically this molecule here, where it's sort of silicon oxygen, you know, and then if I had, you know, oxygen, silicon, CH3, CH3, you know, it's just this sort of motif repeating over and over and over again. These are useful in microfluidics as well. So, you know, essentially what I have here, PDMS, is useful in microfluidics. Basically because you can sort of start it off with a sort of liquid-like composition, and then cast it around a sort of negative of whatever microchannel structure you want to create, pull it off, and then boom, you've created some microchannels. And there are formulations of PDMS that are clear, formulations of PDMS that are gas permeable, so you can create PDMS microstructures and like grow cells in them and stuff like that. And they're, you know, resilient to a lot of chemical attacks for chemicals that we might flow through our microfluidic devices. So it's a pretty remarkable material. All right, now let's talk about polycarbonate. So polycarbonate basically has these reactions happening. So we have something with an OH group, and then we have plus this wacky molecule right here. So a carbon double bonded to an oxygen with two chlorines, and then another OH group with whatever chain we had growing right here. So these react with one another. to produce 2 hydrochloric acids as a byproduct, and then this bond right here, O, C, double bonded to an O, O, and then whatever is going on here. So in a sense, this polycarbonate bond sort of looks like, you know, this side looks like an ester, this side also looks like an ester. It's just the carbon, instead of just sort of continuing directly on the chain, there's oxygen sort of on both sides of this linking carbon. So this is what we call polycarbonate. And polycarbonate, again, polycarbonate is a class of a whole class of molecules. One tricky thing about polycarbonate is this molecule is pretty toxic and explosive. It's highly explosive, corrosive, reactive. It's a pretty nasty chemical. And an example of a molecule here, you know, again, so the polycarbonate that I've described here, you know, like it's sort of this type of molecule here, where we sort of have this difunctional thing right here, OH groups right here that react. One example of this type of thing that has 2 OH groups on it is this molecule right here. So it's like an OH with a benzene ring. And then this connects to a central carbon that then has 2 methyl groups off the side, and then another benzene ring with an OH group. Right, so again, like the OH groups that participate in this reaction here are just the OH groups on the ends of this. But this molecule has a special name. It's abbreviated as BPA, and you might have seen, you know, if you go in the grocery store, whatever, you'll see cans, and the cans might say, hey, you know, this can lining made without added BPA. So the tricky thing is, you know, in even just a decade ago or so, the plastics used to line a lot of our food cans and also some of our other things, these plastics were made, you know, polycarbonate made with BPA added. So BPA sort of goes into polycarbonate. It's also used as a plasticizer, which, if you remember, the plasticizers were those small molecules that go in and sort of disrupt the chain bonding in other types of polymers. Also uses a so BPA also, even if it's not participating in the actual formation of the backbone, it's used as a plasticizer in other plastics. BPA is super problematic. BPA, sort of from a molecular standpoint, is similar to hormones in our body, so such that if some of this BPA leached into your food and then you ate that food, some of that BPA would end up in your body, and this BPA would then sort of bind to some of the signaling molecules or signaling receptors on your cells, and, you know, tell your body like, oh, I have a lot of this hormone present, time to grow in an unregulated way. So, you know, there's some evidence that, you know, BPA is linked to some endocrine disorders as well as some cancers and things like that, because it's basically telling cells to like grow and do a whole bunch of wacky things, when physiologically those hormones should not be given to those cells. So, you know, what's the key thing here? Well, you know, any reaction has this forward reaction, but also has this reverse reaction too. Remember, for polyesters, this reverse reaction was great, right? That's what allowed our plasticware to be biodegradable. For polycarbonates, this reverse reaction is super problematic, because if this reaction happens in reverse, it's going to release a whole bunch of endocrine disruptors into our food and into our body and stuff like that. So, so what's the key thing here? Don't eat foods where the packaging has BPA in it. I can't recommend it, for your health and safety. And especially this reverse reaction increases with temperature. So definitely don't microwave your foods in plasticware. Don't microwave or heat your foods in plastic. You're probably fine storing your foods in plastic leftover containers, but when I do this, I always transfer my food to a ceramic dish before I microwave it, just because I don't want this junk in me. And even if the plastic purports to be BPA free, again, there's other junk in there. I just don't want that in me. Nope, no thanks. Hormone disruptors, endocrine disruptors, don't want that. Let's talk about condensation versus radical polymerization. So condensation reactions are basically what we've talked about today, and we contrast that to radical polymerization, which is what we had earlier, which what we talked about in a previous lecture. So remember, radical polymerization, we had some chain, there was some unpaired electron on the end, and that unpaired electron then attacked some sort of carbon-carbon double bond to then add that monomer to the chain. Condensation reactions are basically molecules with an A and a B, or a sort of paired A, B, B situation like this. So those were the two sort of types of reactions that can form. The way condensation molecules grow is via step growth. And the key thing with step growth is basically any molecule at any time could join up with any other. So all molecules, all are available to participate at the same time. We contrast this to radical polymerization, which is what's called chain growth, where basically growth occurs only at the active end. So that's the sort of distinction, and we'll talk about it. The key thing here is radical polymerization terminates. And you remember how it terminates, for example, if we had one radical and another radical, these can end up forming a covalent bond, and once those radicals have sort of have reacted with one another to form a covalent bond, you're done. That's it. It's terminated. But in contrast, condensation reactions, they can basically we can sort of stop and restart at any time. Right, so let's say I come along, I grow some chain a little bit, and I have this partially grown chain, and then a month later I'm like, oh, I'm not done growing that chain, I want to grow some more. I can add more monomers to that, and those more monomers, given the right reaction conditions, can then continue to grow on these existing chains. So I can stop and restart at any time. Whereas with radical polymerization, unless we have some very heavily controlled ATRP type thing, once we do our reaction, and basically those radicals are going to find each other, and once they find each other, you're done. So we can't really stop and restart radical polymerization in a very convenient way. Whereas condensation, sure, go ahead, just add more monomers and keep growing them. So for radical, we need an initiator. And for condensation, we don't need an initiator. But for both of them, we still need favorable conditions. So for example, if we're talking about polypeptides forming, you can't just take an amine group and put it next to a carboxylic acid group and have it spontaneously react. If that happened, then every single one of our proteins in our bodies would just be reacting all the time to form covalent bonds with every single other every single other protein in our body, right? It's, all of our available amine groups and all of our available carboxylic groups, good thing they don't spontaneously react, because I would just turn into some big jumbled cross-linked reactive mess and none of my proteins would be able to carry out their functions. So, a lot of time for this reaction to occur, we might need some energy as an input, or we might need to raise temperature or drive away water or something like that. We might need conditions. We might need favorable conditions for that polymerization reaction to occur. So that's the key thing here. The key thing with condensation versus radical polymerization is condensation is basically the number of active sites. The number of active sites is continuously going down. What do I mean by that? Well, imagine at the very beginning of my polymerization process, it's a real party, right? It's like middle school dating. Anyone could date anyone. Everyone's available. No one's formed permanent relationships yet. But as these monomers start hooking up and reacting, now, what before I had sort of, any monomer could react with any other, there are tons of interactions that could occur. Once it starts reacting, reacting, now I'm sort of down to the point where, only one reaction could potentially occur. Whereas at the beginning, there were tons of reactions that could occur. So the idea of the number of active sites, right, the number of sort of potentially bondable but as of yet unbonded reactions that could occur, these number of active sites are basically going down. Whereas with radical polymerization, monomers are hopping on, there's still that radical right there. So, basically the number of radicals are roughly constant until all of the monomers are totally exhausted. So, so the number of radicals are roughly constant until exhausted, because basically the number of radicals were governed by the initiators as opposed to how complete the reaction is. So thinking about completeness and how completeness is particularly important for condensation reactions, let's talk about how we might quantify completeness of a polymerization process. So completeness. So one thing we use to sort of quantify completeness is what we call the degree of polymerization. And the degree of polymerization is usually given the variable lowercase p. And what can you think of p as? Well, p, you can sort of think of it as a fraction. And you could think of it sort of as the number of bonds, right? I guess you can frame it a couple of ways. So you could sort of think of it as the number of bonds that have formed divided by the number of bonds possible to form. And so with this in mind, take a moment now, pause and ponder. What sort of range do you expect for P? So pause and ponder. What are limits for P? All right, well, hopefully you've had a chance to sort of think about this degree of polymerization. The limits for P basically can't be any smaller than 0, because the number of possible bonds to form is some non-zero number. But the number of bonds that have formed right at the beginning, as reaction starts, P is equal to 0. And as the reaction goes to completion, all the bonds that have currently formed, asymptotically approach the number of bonds that could form. Eventually, we start off with, kind of a hot mess here, but eventually, everyone finds a partner. Everyone sort of joins together in this chain, except for maybe these two ends here, but usually like the number of bonds that formed in the chain is so much larger than the number of here, P might approach like 0.9999999 or something like that once things here. Or I guess if this wrapped around and formed a ring, then it could be totally complete. Right, so as reaction starts, P goes to 0. At completion, so as we go towards completion, P approaches 1. But if we think about this process here of the number of active sites continuously going down, for example, for condensation polymerization, so sketch what you think as a function of time P looks like for condensation polymerization. So sketch what you think P looks like as a function of time for condensation polymerization. Well, P is going to range between 0 and 1, as discussed right here, as time goes on. So at the beginning, when I had all of those green Legos right here, P starts to sort of very rapidly grow. But as time goes on, less and less and less monomers are able to participate in the reaction. So eventually I asymptote towards this plateau right here. And this process, in order to get all the way up here, this could take a long time. This could take a very long time, right? And theoretically, it might actually never get all the way there. So that's kind of a tricky thing right here. It turns out that you can actually sort of form, you can relate P and the molecular weight to one another mathematically. So P is related to the molecular weight of a repeat unit, and it's related to the molecular weight of chains, the molecular weight of polymerized chains. So what's the key thing here? Basically, if you know the weight of a repeat unit of a chain, right? So for example, if for example, like the weight of a repeat unit in in this right here, like if we knew the weight of a single Lego, and we knew, hey, given this batch of Legos that I have here, if I know the weight of one of these repeat units, and I know, what fraction of those overall bonds have formed, that allows me to predict the molecular weight of the chains that I do. So it's sort of like if you know two of these things, you can predict the third one. So I'll give these things I'll give these things a special name here. Well, the molecular weight of our chains, again, remember we have two slightly different definitions of molecular weight. This one here is the Mn right here, and I'll call the molecular weight of a repeat unit M1. And keep in mind here, this is not necessarily the monomer, but rather the monomer minus the byproducts. Right? Because keep in mind, for example, for basically everything except for everything except polyurethanes, when they react with one another, they kick out something here. So essentially I'm saying, okay, what is the molecular weight of this repeat unit of my polymer? Okay, and in a sense that's sort of the molecular weight of the repeat unit is what I would have for the molecular weight of the monomer minus the molecular weight of whatever was kicked out in the condensation reaction. So what I call M1 is the molecular weight of a repeat unit. In a sense, it's kind of like what the molecular weight of a polymer of chain length 1 would be, and M sub n is the number averaged molecular weight. These are related to P through the following formula. So this relationship is sort of described mathematically as M sub n over M sub 1 is equal to 1 minus 1 over P. So take a moment now and sketch what the ratio of Mn over M1 would look like as a function of P. So take a moment now, pause and ponder, sketch what this curve looks like. All right, so what do you have it? Well, we know that P can range only between 0 and 1. And good thing, because as P approaches 1, this denominator approaches 0, and dividing by 0 means we approach infinity. So basically, as P approaches 1, this asymptotes vertically to infinity. As P approaches 0, we just get 1 over 1, which basically means the molecular weight of the things that I have is just what the molecular weight of the unbonded things are. And I guess, yeah, of course, I guess that makes sense. So this essentially starts at 1 right here. So we get this curve that kind of looks like this. So it vertically asymptotes to 1. So what's the tricky thing here? Well, the unfortunate thing about this is as time goes, generally, when we polymerize polymers, if we want good mechanical properties and things like that, we want to get our molecular weight as high as possible, right? So usually we want this high for good mechanical properties. Right, so we want this to be very high for good mechanical properties. So that means, we want P to approach 1. So that means we kind of want to be in this region right here. But the unfortunate thing is, in order to get P here, we need to wait a really long time. So the unfortunate thing is here, okay, I get most of my polymerization done here, but what I really want is to be all the way out here such that I can get my molecular weight as high as possible, but that takes forever. So there's this trade-off between getting high molecular weight and driving that reaction all the way to completion. So this formula works if we have polymers that polymerize like this. But what if But what if we have the type of polymerization where we have an A and an A and a B and a B, and we have unequal numbers? So what does that mean? Well, basically, what if we have this type of polymer right here, and instead of having this perfectly balanced, 3 reds and 3 yellows, what if I did the somewhat diabolical thing and threw in a couple of extra yellows? All right, so if I had these 3 reds and these 3 yellows, so before I threw them in, I would basically form, I would form one big long chain if I had equal numbers. But if I don't have equal numbers, if I do this diabolical thing where I throw in a couple extra mismatched yellows, maybe I get some polymerization over here. Maybe I get some polymerization over here. But now, even though I threw in more yellow, I actually end up with shorter chains than I would have otherwise, because basically both of these chains are capped off with their yellows and they can't react one another. So when considering the considering the sort of 2 monomer type polymers, so with 2 monomer, like A plus B types or configurations, if I have a mismatch, causes ends to get capped off. Ends to get capped off, and that basically lowers my molecular weight, right? That lowers my molecular weight. So, I essentially find myself in this situation here where, if my yellows outnumbered my reds, everything gets capped off in a yellow, and I'm done. Forget about it. All right, so what does that mean? That means I really want to try to match them as much as possible. It also means that this definition right here isn't quite good enough to really describe, to be able to predict my molecular weight, because in this situation here, I've formed all of the bonds that I could, right? I've formed all the bonds, every single bond is formed, but I haven't, even though I've formed all the bonds, I'm not at this infinite molecular weight. I'm at this somewhat limited molecular weight. So how do we describe this mathematically? Well, we sort of have a modified form. So modified equation for molecular weight. And what does it look like? Well, it still has mn over m1. And now it's equal to this, which I'll call 1 plus r over 1 plus r minus 2rp. So p is still the degree of polymerization, but r is basically a ratio, is a mole ratio of the two types. And basically r is greater than 0 and less than 1, and it's defined as, is basically the number of moles of your AA type divided by your number of moles of your BB type, or your number of your AA type, or sorry, your number of your BB type over your number of your AA type. And it's this when NBB is greater than NAA, and it's this when NAA is greater than NBB, such that no matter what, no matter which I have greater of AA or BB, R is always going to be between 0 and 1. So basically, so what happens here? Well, basically R factors into this equation here, and R can limit Mn over M1 even as P goes to 1. So even if P goes to 1, Mn over M1 only goes to 1 plus R over 1 minus R. So what does this mean? That basically I can allow my reaction to go, as complete as possible, and I can limit, if I want to, maybe there might be some applications where I don't want molecular weight super high. I can choose to limit molecular weight either by controlling the mole ratio of these two things, or by controlling the time that I allow polymerization to occur. So it's my choice, right? As some applications, it might be easier to limit molecular weight one way or the other. Alternatively, this basically means that if I want to get my molecular weight as high as possible, I need to really get this ratio as close to 1 as I can. Whereas if I let R, even if I let P go to 1, I let the reaction occur over a long time. If I also get R close to 1, basically getting P close to 1 and R close to 1 drives my molecular weight as high as possible, which is oftentimes what you want if you want to maximize your mechanical properties or something like that. All right, so thus concludes our discussion on condensation polymerization. Thanks for watching, and good luck with your study of biomaterials.